Hello, everyone. Welcome and thanks for joining us. My name is Sally Ann, and I'm super excited to be presenting our fourth episode in our automated CV pipeline series along with my colleague, Eric. I'm an ML solutions engineer here at SuperAnnotate, and I'll pass it to Eric briefly for a short intro.
Hey everyone, I'm Eric and I'm an ML engineer at SuperAnnotate, and I'll present you the automation part today.
Awesome. Thanks, Eric. Before we get started, just a quick reminder, this presentation will be recorded so you can look out for an email after our call today. And as we go through our presentation, feel free to drop in any questions you have for our Q&A portion. Any questions that we don't get to today, we'll include in our follow-up email. All right. So another quick reminder, our series on automating CV pipelines has 6 epochs, so please join us for the rest to dive deeper into other opportunities for automating parts of your CV pipeline. Next up is going to be box to polygon, and that will be presented on June 2nd. So for our agenda today, we will start off with an introduction to SuperAnnotate and then move on to an overview of video prediction. We'll then dive into specific video prediction tasks and follow that with SA's capabilities for video processing. I will then hand it off to Eric, and then he'll explore the automation suites with you guys, and then we're going to wrap up with our Q&A portion. And before we dive into our topic today, I do want to share a little bit more about us here at SuperAnnotate. So SuperAnnotate was founded in 2018 by Tigran and Bahan Petrosian, our CEO and CTO. We raised $14.5 million in Series A funding last year, and then we brought our total up to $20 million with further investments. We have a global team of over 150 ML enthusiasts, and we are proud to say that we are top-ranked platform in the data labeling category on G2 and have received a high performance badge from them as well. A little bit about our offering. Our offering is split into 3 categories that when combined form a powerful, robust, and efficient suite for all your annotations needs as shown in this slide here. And we'll briefly dive into each of these. So starting with our platform. Here, you can automate labeling, get unparalleled control of your annotation workflow, quickly spot quality issues in your data, and seamlessly integrate into your existing pipelines. Next, our data ops services. So we've screened over 350 annotation service providers, and we chose the top 35 to be in our marketplace. So our handpicked teams of professionals are all trained on our software so that they can flawlessly leverage our capabilities for your project. And then lastly, tying the other 2 together is our MLOps success program. Our DevOps and ML expertise really sets us apart from our competitors. We serve it as an extension to your team, so we're not only supporting your labeling efforts, but we're also setting up and improving your data pipelines. Our dedicated account teams include ML engineers, annotation experts, DevOps engineers, and project managers. So from day one, we're providing you with this white glove service, bringing our best practices to you. So now that we have a good understanding of SuperAnnotate, let's get into today's topic, video prediction. I think something that's commonly assumed is that videos are no different from images when it comes to computer vision. After all, aren't videos just a bunch of images? While this is true to some extent, this is very simplistic and it forgets to account for a very important difference. Video has an additional dimension, time. Videos are not only a sequence of images, but a sequence of images that are related. Each frame in a video contains the spatial information, and the sequence of the frames contains the temporal information. So video level computer vision tasks aim to detect, segment, or track objects with both a space and time dimension. As you can imagine, there's a wide variety of use cases for video prediction. Video analysis can allow for real-time prediction on live video feeds, which has a huge impact on multiple industries. Some of the most popular use cases are found in autonomous driving, surveillance and security, manufacturing, transportation, healthcare, and there's many, many more. So let's take a look at video-specific computer vision tasks associated with our topic today. And we'll start off with video classification. So video classification in principle is very similar to image classification. This task is going to be utilized when the problem statement aims at figuring out what. So for example, Perhaps you want to be able to categorize contents of a video for easier retrieval or be able to predict a video posted that has sensitive content or not. The goal here is to classify the videos as a whole. So to do this, a label would be applied to the entirety of the video. Models are then given the sequences of the images that are temporally correlated so that the model can identify the class of the video as a whole. And for our next task, we're going to cover temporal action prediction. In this task, the goal is to recognize an activity in the video and localize the intervals where the actions take place. In other words, we're trying to figure out the what and the when. So say, for example, you're only interested in sections of a video where a specific event takes place, or you want to build a CV system to recognize various steps in a procedure and ensure that they're happening in the expected order or a certain time frame. These would be perfect examples of video temporal action prediction. In this task, we're interested in the classification of specific intervals, and therefore a specific event will be annotated for that duration that it occurs. So you can think of this as a localized classification. The frames within the time interval will be classified with that action label that is applied. And our last task today, we're going to go over video spatiotemporal action prediction. This task combined with event prediction and object detection. You can think of this as determining the what, the when, but also the where. For example, say you want to be able to identify a car and its position throughout the video. So you want to use spatiotemporal action prediction. The goal of this is to be able to detect objects throughout the video. It's common to track objects throughout the video, and when tracking is done, a unique ID is given to each object in each frame. The model then will successfully match them across the video to summarize a bounding box or a polygon in each frame. And we're going to be showcasing automation for both temporal and spatiotemporal action in just a bit. And then during this demonstration, you'll actually get a closer look inside of our platform. Video prediction comes with its own set of challenges. Among these are the importance of properly processing data, large volume requirements, occlusion of objects, background noise in data, and varying spatial scales of objects. Occlusion is by far one of the most common challenges, especially when tracking objects. When an object is blocked by another object in a video, there's a potential for the algorithm to be confused as the object reappears. So it's really important when labeling to ensure that the identified object is not mistakenly tracked as a new object. Similarly to this, the confusion caused by occlusion is a densely populated background. This could clutter the model, making it difficult to extract features, detect, even track objects. This noise will also make it more difficult to train and optimize your model, and it will be much slower. Lastly, verifying spatial scales refers to when objects vary in shape and size as they travel throughout the video. So this can also confuse the algorithm and lead to generalization errors similar to the other challenges that I already discussed. So for solutions, one of the overarching solutions to these challenges is having a high quality and robust tool. This allows you to digest large volumes of data, and it can also assist in curating the data so that you can limit that background noise. In addition to this, it's also important to choose the correct labeling technique and model architecture to combat these challenges. So, as you can imagine, generating a training set for video prediction is potentially a super daunting task. Without high quality annotations, you won't be able to adequately train your model. And we touched on the challenges associated with video prediction, and a key solution to that was having tooling. Each video contains thousands of frames, and traditional annotation methods can be quite cumbersome for these tasks. At SuperAnnotate, we can drastically improve this experience. Our dedicated video editor allows you to easily manipulate your video stream and label as needed. So we offer a few different tools for this to help you out. So we offer FPS splits that you can specify the rate at which you annotate at. Our editor has a tagging functionality, an event tracking tool for temporal prediction, and bounding boxes as well for spatiotemporal prediction. Our platform uses linear interpolation to seamlessly adjust bounding boxes position while maintaining the same ID, so making those tracking use cases really easy and efficient. And we're always keeping up to date with ML trains, so you can expect more and more features to come. And so we discussed the problem statements the annotation needs for training our three tasks, so that leaves us with prediction. To account for both spatial and temporal information, a hybrid model or architecture can be used. This hybrid model will have two neural networks that feed into one another. First, a convolutional neural network for processing spatial data. This will extract the high-level features. Then, a recurrent neural network for processing the temporal data. The RNN will extract the temporally correlated the temporal correlation between our images. And then the output of the CNN will feed into that RNN layer, which will then produce our labeled output as displayed by this visual below. And there are several other techniques that can be applied to give greater context for model training, like a temporal Kalman filter, also using a long short-term memory architecture. These varying techniques will help us to allow the model to effectively and accurately process both dimensions of the video data. So now that we have a foundational knowledge of video-specific prediction tasks, challenges, annotation requirements, and the modeling architecture, I think it's time to go into the focus of our series, automation. And so with that, I'll pass it to you, Eric.
Thanks, Eliane, for the amazing introduction to today's topic. So let's start. Okay. Yeah, so as Eliane introduced to today's topic, I'll now dive deep into video temporal action recognition domain, and so how we can automate these tasks. And so we divided this task into two stages. The first stage is the unsupervised one. So usually when someone starts with a bunch of videos, he has no annotations yet. So in this case, for the automation, we are aiming to use some pre-trained models so that we can generate some proposals of these temporal events, and then which will speed up the annotation process from them. And then for the stage two, we envision this situation where using stage one, later annotates some of the videos in this large pool of unlabeled videos, and then he proceeds to this stage two automation part where he can use these labeled videos to train, like to fine-tune a model on their data set, so that the proposals of these temporal action segments are actually more accurate, and which in its turn will even more speed up the annotation process. So yeah, let's start from this stage one, like unsupervised scenario when we have a large pool of unlabeled videos. And so what we do for the very first thing is to set up our environment that we'll be using for this automation task. So the main things that we have to install here is changing this CUDA version that basically is provided in the Colab notebooks, and usually it's CUDA 11 nowadays, but this specific framework works pretty well with CUDA 10 and especially CUDA 10.2. And so we are changing this environment to this version, and then we also need to install OpenCV and TensorFlow with GPU support here, so that our mostly our optical flow extraction is getting sped up with this GPU support, TensorFlow and OpenCV. Yeah, and in case that some of you are unfamiliar with the concept of optical flow, it's just it gives some temporal information, extracts some temporal information from video by calculating the perceived 2D motion between consecutive frames of the video. Yeah, so when we have set up already this environment, we are proceeding to our next step, which is setting up your SuperAnnotate team token and then also the project name in these two variables that we have here. This is used by our SDK here in this notebook so that it can connect to our specific project on our platform and extract and later upload the video proposal, the action proposals there. Yeah, so we can quickly set up this and then proceed forward. And this next step is downloading some information that we have. So in the beginning, like before coming to these notebooks, we are usually having set up a video project in our platform. And so there is some kind of this video specific information that we can extract already from there. For example, the video names and their corresponding URLs that we used to attach these videos to our platform. And there are also some kind of other metadata that we can get from the platform, such as video duration. And so, yeah, first thing is that we use this token to connect to our project on the platform and then extract this information of the metadata from there. Okay, so what we do next is, so let's quickly look more specifically on the main thing that we will use for generating the video proposals. And so as you can see here, maybe I can also zoom a little bit so that the figure here is more clear to you. So we have a video, initial video, and we need to generate some kind of proposals here of actions. So actions are supposed to be some intervals of the video which have start time and end time. And then in the end of the annotation, we need to have for the annotation, we need to have these specific segments of videos, and then also labeled to which class belongs this segment, which action happens in this specific segment of the video. And so, but the generated proposals are class agnostic, and they contain only the start and end time and without any class information. That's why we can use a pre-trained model and just it can work on any video and generate proposals there. That's because no class information is expected to be predicted. Yeah, so when we have an input video, what we need to do here, the first thing is that we need to extract all the RGB frames from this video. And then in order to speed up the process, like the processing of this video, we are sampling a snippet, which means a single image from every 16 consecutive frames. So as you can guess, this greatly increases the processing time of the video because we don't need to process every single RGB frame here. This can be done because of this inherent quality of videos, that the consecutive frames are very correlated to with each other, and not really big changes happen in consecutive frames. So yeah, we sample a single frame, and then we also compute optical flows around this snippet that we have sampled from these 16 frames. And this optical flow is not just computed from 2 consecutive frames, but we are going 5 frames right and 5 frames left from this snippet where we are taken, and computing all these consecutive optical flows and stacking them together. And then comes the first part of this figure, the visual encoder part. This is a neural network pre-trained on the very famous ActivityNet 1.3 dataset for this exact specific task. And this network just is a visual encoder. So which means that we are extracting features from both this RGB image and also the optical flow, And hence we are getting, so the spatial network is extracting spatial information from the RGB, and the temporal network is fed these optical flow, stacked optical flows, and extracts temporal information from them and gets these temporal features. And then in the end, these RGB and temporal features are concatenated together, resulting in a single vector. Usually in our experiments, like in our this automation collab, we are using fixed 200 dimensions for spatial network, and also 200 dimensions for temporal. And so, as you can guess, after the concatenation, the final feature vector is of dimensionality 400. Okay, so when we have these fixed 400 dimensional vectors for each of these snippets, we can proceed forward to the step B, which is this first part of which is this temporal evaluation module, which takes these 400 dimensional features of the video. So we have a lot of them, as much segments we have as much snippets that we have extracted from the video, and then feeding these fixed 400 dimensional vectors to this fully convolutional network, which is a temporal evaluation module, which generates 3 scores for each of the fed vector. The actionness, which shows whether in this snippet is an action happening. Starting score, which shows that whether this vector is, like, this snippet is a starting frame of an action. And then ending score, which, as you can guess, shows whether this snippet is an ending frame. Okay, so when we have these scores, we can then feed these scores to this part below, which is the proposal generation module, and which is also this fully convolutional network with some kind of architecture. So the specifics you can also always look up and dive deep into specifics, but yeah, I don't think we need to go that deep today. But it generates proposals, as you can see here. So with start time, end time, we have a lot of proposals generated. And then for each proposals, we also have a feature vector generated, which is used in the proposal evaluation module in the end. So besides generating the proposals, we also need a confidence score for each of the proposals, so that we can later judge whether to use that proposal or not, how much the network is confident that indeed there is an action happening in this segment of video. So these generated feature vectors for each proposal are fed to this fully connected network, which generates a score for each proposal, which corresponds to the confidence that there is an action happening here. And then for the final step, we can perform a soft non-max suppression of the proposals. So it is soft because it just lowers the score for the redundant proposals and not exactly eliminating them from the list of the proposals, so that we can later decide how to filter these proposals correctly. Okay, so we have basically introduced and maybe understood the whole concept of how this network will perform over our videos, so that we can now go step by step and see how the exact pre-processing and also these inference steps are divided in this automation notebook. And yeah, so the very first thing is building this ActivityNet JSON, which is done by running this script. So why do we do this? So for this purpose, we are using in this automation collabs the MMAction2 library, like the framework that supports various both temporal action proposal models and spatiotemporal action proposal models. So that's why we're using this framework for both inference models and also for later for training. And this framework supports this ActivityNet 1.3 dataset format for the videos that you have to run it on. And so we are making a dataset format of this ActivityNet JSON, of this ActivityNet dataset out of our own videos from the platform, and which is accomplished with this build ActivityNet JSON. Next, because in our from our tool, we exported these informations about the videos, like the names and then the corresponding URLs where our videos reside. So we are running this download video script so that the actual videos can be downloaded from the URLs. And also, after the download, we also measure the specific duration of videos in seconds, and also we calculate the duration of frames, which means how many frames exactly are there in this video. But as you can guess, it depends on the frame rate of these videos. And updating the ActivityNet 1.3 format JSON that we generated in the previous step by adding these fields there. And next, when we have downloaded already the videos here in the Google Colab, we are running this script to extract the frames out of our videos so that our videos are transformed to a bunch of images. So you can imagine that there are, for example, 2000 frames in these videos. So we are extracting all these frames and writing as PNGs here in the Colab. And then when we have all these images, we can proceed and run these scripts. So which you can notice that are provided by this MMAction2 framework for the pre-processing purposes. So yeah, we're running this script on the extracted frames to generate the optical flows that will be used in the visual encoder that I introduced in the previous step. Okay, so when we have these pre-processed videos already, the RGB frames and the optical flows, we are generating raw frames file list, so to say, which is used by the framework. So we are generating just a test file list, which includes all our video names, and after a white space, we are writing the number of frames in each video. So each video takes one line, and it's basically the name of the video and the number of frames it has. It is just used by the framework for the inference and the proposal generation thing. Okay, so what we do next is we download from the OpenMMLab the pre-trained weights of the time segment network, temporal segment network, which acts as the visual encoder in the figure that I showed. And later, when we have already the pre-trained weights of this temporal segment network, we are running it on the extracted frames and getting the RGB features of each video. So as you can recall, the first 200 dimensional vectors represented the RGB features of each video. And so we are extracting them. And by the next step, which is this one, we're doing the same thing, but this time we feed the stacked optical flows and extract the temporal information, like the other 200 dimensional vectors, which correspond to the temporal part and which we get from these optical flows. And for this step, we are just concatenating this RGB and flow features together and getting these 400 dimensional vectors that will be later fed to the temporal evaluation module. And then, so again, this script just performs some kind of post-processing and writes the information about each video in the test.json file, which will be used for the, again, for the proposal generation. So this is just an MMAction2 framework specific thing that we need to accomplish before running the proposal generation. Okay, so when we are finished with the pre-processing and also the post-processing of the features that we got from the visual encoder, we are downloading the weights of this temporal evaluation module, which we will use to generate the actionness and start and scores that I talked before and showed in the figure above. And so with the first step, we are getting the weights, and then we are running this script to use these downloaded weights and generate the scores for each of the video. And then we are again utilizing a script which does the main job, like the proposal generation, and uses the scores generated above of actionness, start and end to generate actual proposals that we need. And also afterwards, it does the non-maximum suppression, soft non-maximum suppression step to get the final proposals with their suppressed confidence scores. Okay, and finally we reach to the final block of our automation notebook, which is upload of the proposals to the tool. First thing that we need to do here is to set a confidence threshold. So as you can guess from the previous steps, as we generated like this confidence scores for each of the proposals, we usually we don't need all of these proposals in the tool, because that would be a lot of them generated there, and also the low confidence proposals will be pretty redundant, and also most of the times they wouldn't have any use. And so we are setting up a confidence threshold, which we'll use to filter out these low confidence proposals before the upload process. So the closer the confidence threshold to 1, the less proposals will be uploaded to the tool, but the uploaded ones will most probably be very good ones. But if you need more proposals and you want to filter them out by hand, like by looking the proposals yourself and then decide whether to filter or not, you can always decrease the score, and the closer it is to 0, the more proposals you will have there. Okay, and then we come to the final part of the and which is this script, which takes all of these proposals that we have generated here, and then filters out the proposals that have confidence scores less than the threshold that we set. And next builds pre-annotation JSON files for each of the videos in a format supported by our platform, so that you can later upload them as pre-annotations of your videos. So what we do here is basically that. And at last, we are just uploading all the proposals that we have generated by this single command here. And yeah, they will be present in the tool afterwards. So yeah, as I said, as we imagine, you are running all this notebook with this unsupervised scenario to get proposals for your videos, and then you usually go to the tool and start the annotation process after these proposals. And then when you have annotated some part of your large pool of videos, so to say, for example, you have annotated 20% or 30% of your videos, you can try to proceed to our next automation Colab notebook that we provide, which basically does the second stage of this pipeline, which is using these videos that you have already labeled to train, like to fine tune the temporal evaluation module to your specific data set so that the proposals are much better. And yeah, even the confidence threshold can be set to a significantly low number, and that wouldn't usually result in bad proposals being generated. And yeah, this would greatly even more speed up your annotation process afterwards. So yeah, let's again quickly go through the to the second notebook, because most of the parts are pretty similar to the previous one. So the environment is exactly the same, and we are not using any new libraries or frameworks here. And yeah, maybe we can quickly pass through this one. Again, setting up SuperAnnotate token and project name for the training videos, like where exactly these videos, like both non-annotated ones and the labeled ones, reside exactly in our platform. And then we are again like using this token to connect to this exact project, export, and then export the data, both the annotations of labeled videos that we'll use to train the temporal evaluation module, and then also the metadata for both the labeled and unlabeled videos that will be used exactly the same way as we did in the previous notebook. The figure is the same as we are using the same architecture as before. We will be just training this temporal evaluation module for several epochs so that to fine tune to our specific video data set. We usually don't train the visual encoder because the pre-trained version is a pretty good feature extractor, and the fine-tuning of it usually takes much longer than the fine-tuning of the temporal evaluation module, as it is a pretty small one. And yeah, so, but of course it can be done with little tweaks in this script in case you need also to fine-tune these models. They can lead to slightly better performance, but only fine-tuning the temporal evaluation module is usually enough. The first two steps are basically the same. So we are building all the data that we exported from our tool. We are converting them to this ActivityNet 1.3 dataset format, and then again downloading videos from the URLs that we get from the platform, and then again updating the duration, both duration in seconds and duration in frames. And yeah, again, we are extracting the frames from each of the videos, and also later we calculate the optical flow for every consecutive frame that we have already extracted. We proceed forward this time to generate. So again, we are generating these file lists of the video names and then the frame numbers, but we have to generate for 3 different sets: training, validation, and test. Training and validation will be used only for, so they will contain the labeled videos only, and we are extracting 10% of these labeled videos and adding them to the validation set, so that during the fine-tuning process of temporal evaluation module, we can actually look at the performance of the training so that we decide whether to tweak some hyperparameters or not. Yeah, again, we're downloading the pre-trained weights of the temporal segment network, which acts as the visual encoder there. And what is different from the previous part is that we are running this script for the 3 sets that we have separately for train, validation, and test videos. And for the first part, we run for 3 of them and extract the RGB features of videos in each of these sets. And next, we extract the flow features, the optical flow features of each of these videos in each of these sets. And hence, again, we are getting 200 dimensional vectors for RGB features and 200 dimensional vectors for flow features. And again, we are concatenating the RGB and flow features to get this final 400 dimensional fixed feature vectors. And this time, again, we are calling this split annotates.py script to generate. So in the previous step, we only generated this test.json file that we used to run inference on. But this time we are splitting into train.json, validation.json, and test.json, which, yeah, you can guess where are used each one of them. So when we have all of these steps done, we are training. We need to train and evaluate, so to say, the model, or validate mostly. And we are running with the default hyperparameter setting that we have. And you also can tweak these hyperparameters if you need to, but usually the default ones are pretty good in our experience. So the config file resides in this path. You can navigate there and change the hyperparameters. And then you just run this training with this validate option, so that after each epoch, validation score is printed. And next, you are using the trained model to generate the proposals with this newly trained temporal evaluation module. And we are doing that by running this script. You can change the pre-trained weight with the other number of epochs. So when you look on the validation results and see that the best checkpoint, for example, is not epoch 9, but epoch 6, you can swap that with epoch 6 here and run with that weights. And the final part is exactly the same. We are setting again a confidence threshold so that we can filter out the, so to say, useless annotations, useless proposals that we have generated, and running this script, which is kind of the same as the previous one, that filters low confidence scores out and then generates JSON files in the specific format of our tool. And again, for the last, we are calling this one line of our SDK to upload the generated proposals to our tool. Okay, so we have finished these 2 Colab notebooks that cover all the pipeline of this video temporal action recognition task. And so because this both, even the inference part takes pretty long time to do, it won't be suitable to do live demo here, but I have prepared a video on which I have run the unsupervised part before this webinar, and we can have a look. So so that you can get an idea that usually what will you see in the tool after you ran this notebooks. And as you can see here, here is the video which we can play. And in the video, just these cyclists are racing. And below, you can see the proposals that we have. So pretty, so I used the confidence threshold 0.5, so I didn't change anything. And as you can see, there are pretty much overlapping parts here. And one other thing that you can notice here, as I said, is that each of the proposals is just the start and end time. So for example, if we come to this one, as you see, we have generated just a proposal with start and end segments. And one thing that the annotator is left to do after this proposal generation process is to look at each of these proposals and decide what class should it be labeled to, which you can, for example, start, check a single proposal and then run the video to see what happens in this video mostly. So most probably, yeah, you can come and, excuse me, choose a class. For example, we can choose writing. And yeah, so it becomes labeled as the writing action happens mostly in this segment uh, of the video. We can, and the job of the annotator here becomes looking in each of these segments and assigning a specific class to these segments, or otherwise there can be also some kind of redundant proposals here, which shall be removed. And again, for example, if you decide, for example, that this one is a pretty long one, and most probably, so most probably these long proposals, for example, this one are not describing a specific action, and just a lot of things are happening here, and you can't label to a specific class. In this case, you can just remove this, for example, by clicking the right click and then delete instance selection from there. And yeah, as you can understand, by using these automation notebooks to generate the proposals is speeding up the annotation process a lot by providing these start and end times, because the annotator just needs to look at these proposals and then deciding to delete, and then decides to delete or to classify, which takes significantly less time than if the annotator started from scratch and needed to look through the video several times, like multiple times, and for each specific action decide the exact start time and then end time of the of each of these sections. After using the training notebook, these start and end times of the proposals are getting much more accurate. And even if only using the unsupervised one, the annotator also would need to tweak, like change the start and end times of each of these segments, which also is pretty fast compared to starting from scratch. But using both notebooks, like also the training one, will even mostly eliminate this start and end time tweaking from the pipeline, and the annotation process will be much faster. Okay, so that's all that I wanted to say today for the automation part, and maybe we can jump to the Q&A session.
Yeah, absolutely. Thank you for that, Eric. Really impressive presentation. I can think of a lot of use cases where this automation would be really powerful. And it's been really exciting to see, video use cases grow and the technology growing and how our platform has mimicked that. And our automation capabilities just really tie it together. So really, thank you for showing that off. We do have some questions. I think the first few are for you, Eric. So starting off with, what's the best way to keep the consistency and accuracy of the annotations?
Yeah. Okay. So from my experience, I would say that there is no general rule of thumb here for all annotation scenarios, as you can guess, and it mostly greatly depends on the task that you want to accomplish. But generally, for example, setting a multi-stage uh, or multi-level annotation process, like annotation and iteratively a QA process followed by it, would yield to high quality annotations. And uh, although it is much more costly and time consuming, so I can also think of an example here so that you can more vividly imagine the situation. For example, you're again annotating a video and you need to set up this, like annotate the start and end times and classify. Uh, so you are doing this the video temporal action recognition task, and you for autonomous driving scenarios. You can for example, split and do first all annotate all the actions that a pedestrian is performing, and uh, and then QA these annotations when they are finished. And then for the stage two, you can annotate or all the actions that cars or vehicles are performing, and then again QA uh, these annotations. So this helps the annotators to concentrate more on a specific task and don't look on other things that are happening in the videos. So which uh, which yields usually a good a good quality of annotations in the end. And also besides this, so this was the costly part, and besides this you can also be assured that your specs that you are providing to our annotators are well written, and they understand it pretty well before starting the annotation process. And yeah, this will also ensure the high quality of the annotations in the end.
Great, thank you. And another one that I think is for you is, what's your suggested way of overcoming, human introduced or annotator bias?
Mhm. Yeah, so this is again, I would split into two parts. And for the first part, if the annotation budget is not a big problem, the I would suggest to assign the same data set, for example, to different annotators to annotate, and uh, different annotators or even different groups of annotators. And then in the end, when they have already annotated uh, uh, these data sets all separately, we can aggregate in the end all their annotations with the following way, using the majority voting procedure, so that in the final aggregated annotations, uh, all instances that the majority of the annotators annotated the same way are only that instances are aggregated. This can be usually accomplished with a consensus tool that we provide. For example, for the images, out of the shelf consensus would work. But for example, for videos, it can be a little tricky. And but with some modifications and tweaks, additions to the consensus tool, it can be accomplished as well. Uh, Another thing is again, so for otherwise, when the budget is problem, again, you should have clear instruction sets provided to the annotators. And also another thing that you can do is to collect representative data set, for example, or use active learning to iteratively select which of the data would be annotated next. That also would help to counter this issue in bias. And yeah, so that way you can like improve your data iteratively.
Great, thank you. And unfortunately, we're just about at time, so we'll definitely send out the answers to the rest of those questions in our follow-up email. And again, this is a series, so please join us for our next episode on June 2nd. And thanks for joining.